see us there. Welcome to the computer security seminar. Today's speaker is Dr. Peter Mork from MITRE Corporation, and he will talk on database assurance, anomaly detection for relational databases. Peter.
Thank you. So what I'm going to talk about today is part of a much larger research project at the MITRE Corporation. The umbrella grand challenge that we're looking at is mission assurance. Basically, the idea is we know that there are adversaries inside our networks, adversaries inside our applications, adversaries inside our systems. Despite the fact that we have these adversaries all around us, we have to continue doing whatever our missions are. Some of those missions that MITRE is sponsoring may have some sort of military bend, but the mission may be to provide health care to the nation's population. When adversaries get inside those systems, we have to continue operating regardless. And the talk that I'll give today is specifically how do we keep our database systems up and running so that we have the least amount of damage when the adversaries get inside. So as a background, why am I even looking at relational databases? These things are pretty much everywhere. They're the trusty back ends to our whiz-bang applications. So at MITRE, we use a relational database back end for our internal time reporting system. So whenever we fill out our time card, it's going into an Oracle database. Transcom, the nation's tracking for, or uses databases to track troop and material movements throughout the world. So the Global Transportation Network and the Global Decision Support Systems both rely on relational databases. As electronic medical health record systems become available, they too rely on these databases. So anybody who's got these things, and I'm going to argue that that's pretty much everybody, they need to be worried about when their data assets become compromised. And the sorts of compromises we're talking about here are exfiltration, or an adversary trying to leak the contents of that database either to themselves or to a colleague, as well as manipulation attacks, attempts to change the contents of the database. Although on this talk I'm going to look just at exfiltration because modification or manipulation attacks are the focus of this upcoming year research. And I would advise you still use all of the regular standard database security measures. This is just that extra little bit of icing. But unfortunately, even if you are really, really good at database security, that's not everything that you need. It's really, really hard to get the configuration just right. And even if you do, you still are susceptible to insider threats. So if there are people inside the organization who know what your security configuration is, they're going to be the ones who can figure out how to get around it. Or maybe they're admin people who have a legitimate reason to get around those things. So that's an attempt at setting the stage for why relational databases are of interest. I'll spend some time motivating what sort of attacks adversaries can launch against these database systems, look at where we do our monitoring in terms of finding anomalies, look at the techniques we use for detecting that anomalous behavior, go over some experimental results, and conclude with a couple of comments on what sort of expectations we're making in order for our system actually to do what I advertise here. So first, what's the big deal? What can adversaries do with these database systems? So who here feels that they could launch a SQL injection attack? Okay, this is not a common topic. Glad I threw some stuff in. So first off, as I'm going through some caveats, the data that I'm showing, they are real data. They're real medical discharge records. However, they've already been anonymized, so that concern is taken out. The IDs and passwords that I'm showing are completely fake. We just made them up out of whole cloth. And the last thing is this application, the developer who produced it for me was instructed not to pay attention to security, just get the job done as quickly as possible in an attempt to sort of mimic the sorts of things that happen every day on real systems. So first, application works like you'd expect it to. I put in my user ID, I put in a password, and I'm able to say, see the medical record. Everything's working like it's supposed to. What is it doing behind the scenes? On the web server, there's some code that says select everything from this table called core, where ID equals some identifier that's going to be provided by the user, and the password equals something provided by the user. So when you put in your user ID and password, that gets converted into this code to be executed on the database platform. Select everything from core, where you have my ID and my password. What happens, however, when I go into that field and I put in a user ID, but a single quote followed by a semicolon and 2 dashes. In that case, I still get to see the medical record. What's going on behind the scenes? So this was, again, what the web server is doing behind the scenes. And when that code gets assembled by the web server, you get select everything from this table called core, where the ID is my ID. The single quote ends the string. The semicolon ends the command. The 2 dashes are a comment, so that last line, what I put on the last line is simply ignored because it's now a comment. As a result, I get all of the information about this user without ever having provided a password. That's bad enough, but it gets worse. We can start doing some more probing. So this first attempt, I've just put in and false. The goal is I don't want anything to be returned by the query that the web server was intending to run. Instead, I'm going to union all. I'm going to add in my own query. And first, I'll just try selecting 1. And when I attempt that, I get this error message, unable to retrieve data. This means most likely the SQL that I wrote didn't line up. When you're doing this sort of SQL injection, what comes before the union has to have the same number of return values as what comes after the union. And in my first attempt, I didn't guess correctly. So I'll just keep running a few more attempts until I find one that works. In this particular case, I had to keep adding numbers until I got up to 129. There were 129 columns being returned by the web server's query. I need to return 129 columns in my query. Now that I've done this, now I get back actual results. And I get back a couple of things. Might be a little hard to read some of the fine print. Not only do I know exactly how many columns I'm supposed to be returning in whatever query I want to run, but I'm also discovering where each one of those columns lines up on the form because I'm getting 61, meaning for the patient ID, meaning that the 61st column got placed there. Age was 3, etc. With that information, I can now do many more interesting things. So the next query that I'm going to run conveniently has exactly 129 columns that it's returning. Almost all of them are just ones because I don't care about them. The important thing is I can now ask for the name of a table from the database's system catalog. Basically, every major vendor out there supports the information schema.tables as part of its features. So this is going to work on pretty much every database platform out there. And what's going to happen is I'm going to get back the first table name. So when I run this, I scroll down the form and I find that in the place of the state postal code, I now have this information that I wanted to pull out of the system catalog, namely that the first table alphabetically is administratable role authorizations. Next, now that I've gotten the first one out, I can do the same thing and just say, give me the next one by saying, give me everything that's bigger than that one, and continuing to sort. In this manner, I can just iterate through every record in this system catalog and find out the name of every single table in the database. Once I've done that, I can do the same thing looking at columns. So there's another system catalog that tells me the names of the columns. I pick out all of the columns for a particular table, just pulling out one at a time. What does this let me do? Well, I've learned that there is a table that's called core. That seems to be an interesting one. I've determined that that table has exactly 129 columns, which corresponds to the number of columns that I know that the web application is generating, and that there's a couple of interesting columns in there, ID and password. So as the adversary, I now have a pretty good idea of what query is being produced on the server side. I'm basically able to reverse engineer what we here know as the actual web server code. What can we do with that? We can now retrieve a password. So by doing this, instead of reading through the system catalog, I'm going to pull out the password field for a particular ID. And when I run that query, I get back out the password. And it's not advisable security practice to use the same password on multiple different sites, but I'm betting that most people still do some form of that. Now that I've gotten the password here, I can now go try that login and password on a whole bunch of other systems and see what I can stumble across. It was an awful lot of work, though, to get just this one password. Here's a different interface to the same underlying database. This one lets you do sort of aggregate roll-up style queries. So you can query by gender, race, age, and what it's supposed to do is when I run the query, it tells me for this particular subset of people how many had a particular diagnosis. So there were 41 people who had the diagnosis code of 65421. I'd have to go look that up in ICD to figure out exactly what that code means. But it's supposed to be intended to be used by statisticians who are trying to get a feel for what sort of diseases are prevalent. Instead, I'm going to take that same query, and I'm now going to run it through Tamper Data, one of my favorite Firefox plugins. So when I hit search, up pops the Tamper Data pop-up, And I can see over on the right-hand side that some of the information, such as gender and race, is being passed back to the web server as these table attributes, female and race. That's not the information I want, though, so having already mined the system catalog, I know that ID and password are valid fields. Let's just hope that they're not checking very carefully on the web server side that I'm not trying to pull out those attributes. Sure enough, there's no error checking that's going on. Now I've gotten a dump. It scrolls way off the bottom of the page. I've got every single user and every single password from the entire system in one query. So hopefully I've convinced you that these database systems, there's a reason to protect them, that the threats that can go on are pretty severe. I focused there just on SQL injection. This is a list of the top 10 database threats that was put together by the Imperva Corporation. We want to do more than just stop SQL injection, though. There are people who are legitimate insiders who have been given more privileges than they strictly need to fill their role. We want to prevent them abusing those excessive privileges. There are people like admins who have a lot of privileges and need them for a very good reason, but they still might abuse those privileges. We want to stop that sort of activity. We want to stop people elevating the privileges that they were given to be able to masquerade as somebody with higher privileges. I put OS vulnerabilities with an asterisk because it is our contention, and we'll test it with a red team exercise, that if there are holes in the OS, but you want to get information out of the database, the easiest way is still to go through the SQL engine and not try to pull the bits off of disk and reconstruct it elsewhere. And then there are other liabilities to the system, such as vulnerabilities in the protocol that the applications communicate back to the database through, or if people have crummy passwords, then somebody from the outside might be able to masquerade as an insider. Things we're not tackling that are still important, having audit trails. We actually rely on the audit trails in order to do the anomaly detection. We got nothing to say about denial of service, and if your backups are somewhere where somebody can steal them, that's entirely out of scope as well. So that's what's the big deal, why I think that defending these database systems is an important thing to do. Next, I'll look at the architecture of the database engine and describe where it is we're going to start doing our monitoring before talking about exactly how we do the monitoring. So here is a picture of a database stack. At the top you have the applications or the SQL interfaces that are running on the database. The SQL commands get fed into a query parser. The result of that is passed off to a query optimizer that rearranges terms inside the query so that you can push your selects down so that you're throwing away unnecessary data as quickly as possible, etc. All sorts of things happen inside the plan generator and the plan cost estimator. Then the query plan is handed off to an evaluation code, and that needs to go through and deal with managing transactions, figuring out how to get the data off of the file system, maintaining the main memory buffers, etc. In terms of related work, most of the focus so far has been on the layer of SQL commands. So for the database activity monitoring vendors that are out there, they really tend to focus on looking at SQL commands. Some work that came here out of CERIAS also looked at SQL commands. I'd say about half of the academic work focuses on the SQL commands. It's attractive because it sits entirely outside the database. It's really easy to get your hooks into. But I'm going to argue that we can get more information from deeper levels of the database system. But first, other places that people have looked. One interesting place to look is inside the transaction manager. Once you're down at that level, you know what the sequence of reads and writes has been. That's a lot of information at your disposal. The drawback is twofold. First off, you can only do your monitoring after the query has run because you have to observe the reads and writes, and by then it's too late to stop the attack happening. The second limitation of the transaction manager is because it's looking at the interaction of reads and writes, if there are no writes, it can't stop it. So attempts for exfiltration are not going to work very well at the transaction manager. There's been a little bit of work on looking at the system catalog. This helps you detect privilege abuses, but not much else. And then there's been some work on file access methods. This is very similar to other attempts to stop insider threats because you're monitoring the file system. But again, you can only do it after the fact. You can do it for detection or forensics, but you can't do it for actual prevention. So where instead we plug in is between the query optimizer and the query plan evaluator. And the reason for doing so is by the time the database engine has gone through the task of optimization, it's created a lot of useful information. At that point, you have good guesses about how big the result's going to be, how expensive it's going to be to compute that result, and you also have all of the information about specifically what tasks are going to be done in what order. And that's great information from the perspective of building up profiles of legitimate activity. So what features are we explicitly pulling out of the query optimizer? So the first thing we can get is we get an estimate of how much data is going to be read from each table. It's going to depend on the exact query. It's dependent on the statistics that are being maintained. So it's just a guess, but it's usually a pretty good guess. We get an estimate of the number of records that are going to be returned by the final query. We know exactly which access plan is going to be used for each table. Are we going to just do an exhaustive scan of the entire table, or are we going to use some sort of index to look up just the values that we're interested in? I won't go through all of the rest of them, but there is a myriad of other features, which attributes are being returned, what algorithm is being chosen to do any joins that are being performed, which user or role is purported to be being used, etc. To tie this back to some of the related work coming here out of CERIAS, related work by Camera and Bertino and one other name that I've forgotten. My apologies if that person is here. What they were looking at was what's being returned in the output, does it appear in the selection predicate, and what is the role? So they're looking at that subset that you can get out at the SQL command level before it's gone through the query optimization. So then, now that we know where we're plugging in and what sort of information, how do we detect anomalous behavior? First, sort of a side trek, if you will. Marcus Raynham has a blog that he rants in every once in a while. And one of the things he's put together is the 6 dumbest ideas in computer security. And he says that one of the dumbest things you can do is enumerate badness. And he uses this graphic to justify that. He says, look, by this point in time, the illegitimate activity exceeds the legitimate activity, and the illegitimate stuff just keeps growing. It's foolish to try to track all of the possible things that might go wrong when there's only a handful of things that you know are right. So instead, enumerate the stuff that you know is right, and everything else then, by definition, is at the very least suspicious. And so that's a tack that we've taken to heart. We're just going to enumerate the goodness and flag everything else as suspect. The technique that we're going to use is called cross-feature analysis. We kind of backed ourselves into a corner when it came time for building our profiles. When I talked about what was in the query optimizer and the sort of information we could get back out, there were things in there that were just straight numbers. Things like how many records we're going to return, how long it's going to take the query processor. For those sorts of methods, it's easy to compute a distance so that you can decide how far you are away from where you expected to be in some high-dimensional space. But once you start talking about things like, am I going to do a hash join or a sort merge join? I can't tell you if that corresponds to a difference in 50 tuples, 175 tuples. There's no good distance metric, so we had to scrap any technique that relied on distance metric. Similarly, we only have legitimate examples. We're only profiling the goodness, so we have to use only those techniques that allow us to build our profiles up only on known good behavior, a single class algorithms, these are called, of which there's only a handful. And once we put those two constraints together, the only thing we were able to find was this technique called cross-feature analysis. The way this works is, during the profiling step, you accumulate all of your historical data. You go looking through query logs or through performance tests. You then extract those features from the query optimizer, and then you build a decision tree for each of the features based on all of the other remaining features. So if we have 100 features that we're extracting, we build 100 decision trees. Each one predicts one feature based on the other 99. And the idea is that if in fact there are strong patterns, then knowing 99 of the features, you get a really good guess of what that last one is going to be. Then at decision time, at runtime, when a new query comes in, we extract the features just like we did before, but this time we're going to predict them using all of the remaining features and the decision trees that were built, and then we can classify as normal or suspicious based on how many we were able to get right. So let me walk through some examples of how this works, not using query optimizer output, but something that's a little bit easier on the eyes. We're looking at shapes, numbers, and colors. So those are going to be the sorts of features that we're looking at. And at runtime, we need to classify this red square with a 0, as well as these other two squares. And give you a moment to stare at those and decide for yourselves which ones you think look as legitimate and which ones look anomalous. So the first step now, we need to extract the features. So in this case, the features are pretty simple. For the first shape, we extract that it's a square, it's red, and the number is 0. And we similarly, for each one of our examples that we see, we extract all of the features. In our system, actually, this is being done from the query optimizer, but for this example, we'll use these features. We then construct models for each of the features. So the first one we'll construct is the shape feature. So across the bottom is the thing we're trying to predict, that's shape, and the decision tree says if you observe these things, this is what we expect to see. So to build this particular one, we first noted that color is the most predictive of shape, followed by number. That's just why those appear in that order. Then if we look at the far left-hand cell, when we observe red and the number 0, in every single one of our test cases, it was a square. So we're going to say put 100% for square in that particular one. A more complicated one is over here. If we see purple and 0, we saw 4 times that it was a circle, 2 times that it was a square. So we'll just put in 2/3 and 1/3 respectively. So that was the decision tree for shape. We build a similar one that tries to predict the color, and then one more that tries to predict the number, although in this case there was nothing that was particularly predictive of number, so the profiling software just returned this brain-dead sort of decision tree. Now let's look at an example at runtime. So all of this previous stuff was done offline ahead of time. Now the system has been turned on. We observe this new query that comes in that's a red square with a 0. So we first look at the color because we want to predict the shape. We see that it's red, and we see that the number is 0, so we predict that it should be a square. We see that the shape is a square, so we predict that the color is most likely red, but it might also be purple. And finally, we don't have much of a guess for 0, but we'll throw in our 53. If we take just the average of those 3, we get 76%. We'll call that high enough. I'll get into a little bit later how we decide what's high enough, but we'll classify this one as legitimate because it looked pretty good. Now we'll look at the green square with the 1, walk through a similar sort of pattern here. We see that it's green, we see that it's the number 1, we predict that it should be a circle, and it's not. We look at the shape, we see that it's a square, it should be red or maybe purple, but certainly not green, and then we see the number 1. So we average these together, we get a pretty small number, so we'll say this one's garbage, we're going to reject this query. Then the last one that we have is this red square with the 1, so walking through that one as well. We're not exactly sure what shape it should be, but a square is pretty plausible. When we try to predict the color, red's a good number. Try to predict the number. We get an average that's kind of in between because this is not quite as common as that first example that we looked at. So there's actually some gray area in the middle where we're not really quite sure whether it's legitimate or not. To relate this back to, here we go, there's the name, Camera, Terzi, and Bertino. This is the most similar related work. In this one, they were looking at the SQL that was coming in. The features that they were extracting were which relations were appearing in the from clause, which attributes were in the where clause, and which attributes were in the select clause. So it's a subset of the features that we're looking at. For their prediction phase, what they were looking at, in the presence of roles in the database for the security system, you start with the role and you use the role to predict all of the remaining features, and you're basically measuring the distance, because in this case, we're just looking at you count the relations, count how many things were in the select clause, etc. Nice, well-formed numbers, distance metrics make perfect sense. In the absence of roles in the database system, it gets a little dicier. The first thing you have to do is predict a role based on the features you've observed, then turn right back around and say, okay, this is the closest one that matches, but how far are we away from it by going through the same beginning step? And this gives them a pretty good ability to identify anomalous behavior. But once we add in all of the extra features from the query optimizer, we can get that next step. So let me justify that what we're doing is on the right track in terms of our experimental results. So first, the setup for the experimental phase. We obtained a copy of the internal time reporting system. So it was actual internal data from the Oracle system. To construct the legitimate workload, we got a copy of 28 days worth of normal employee activity. So logging in to look at their time card, update their time card, etc. We just looked at the actual select statements. We didn't worry about the updates yet. And then we created 1 year's worth of the daily and weekly reports that are processed for all of the various budgeting people who have to figure that stuff out. In terms of synthetic attacks, what we did was we have all of those legitimate feature vectors. We randomly create feature vectors by sampling from the observed distribution of values. We looked only at the observed values because if we look at all possible values, many of the features we create will inadvertently touch stuff we've never seen before, and it would automatically get flagged as an anomaly. That would make us look a little too good, so we wanted only to focus on the values that we actually observed in the legitimate feature space. And what this synthetic attack workload really does is it doesn't prove that our system is going to stop attacks in the wild. what it shows is, are we creating really good patterns? Are we creating patterns such that if you pick a random point in this high dimensional space, just randomly create this feature vector, are you more likely or not to land by chance in something we've classified as legitimate, or will you end up in hopefully a vast sea of stuff that we flag as not legitimate? The next thing that we did after we put together our synthetic attack scenario was look at some real attacks. So I assembled a security team, and they generated a list of 8 possible goals that an adversary might have if they were trying to attack this system. So the adversary's goal might be something along the lines of, look for employees who are likely to be recruitable. And those employees might be people who have a lot of foreign travel, who look at their time card at odd hours, who work a lot of weekends in the office, things like that. Another goal might be to see if we can get the passwords out of the system, just like I did with the earlier SQL injection attempt. Once we knew what the adversary's goals were, we then asked the SQL experts on the security team, okay, come up with plans. What query would you try to run in order to accomplish those goals? So we mapped each one of those goals into at least 3 different SQL attempts, either downloading all of the data that you wanted in one query, maybe trying to sneak out a record or 2 at a time, in a bunch of little queries, different ways that you could accomplish the same thing by doing some post-processing by the adversary. And then those 8 goals ended up being 33 different SQL injection attacks. I'd like to say that we had the time and money to develop even more, but each one of these attacks is a fair amount of effort in order to actually put together, which is why we needed to back this up with some synthetic results as well to get a feel for the space. So first thing we looked at is performance. If this adds a huge amount of overhead, nobody's going to touch it. So in terms of the performance time measured in milliseconds, if you just run without any of our stuff plugged in, the query optimization task takes about 770 or so microseconds, just under a millisecond, for each query to run. In our case, we built the profiler actually inside some Java code relying on open source stats packages. As a result, there's some inter-process communication because we're using the Postgres system, which is written in C, so our C code had to go out and invoke this Java code. So there's some inter-process communication that happens. That costs you about another millisecond. And then there's the actual work done by the profiler to test the query, and that runs in about 50 microseconds. So in terms of could you deploy this in the real world, if you re-implement the stats, the piece of the stats package that we're using inside C code directly, your overhead's going to be another 50 or so microseconds. I think that's entirely reasonable. If, however, you need to rely on a separate machine, you don't have access to the source code because you're using Oracle or SQL Server, you're going to get this inter-process communication overhead, and it's going to roughly double the time for optimization. So that's probably that threshold where you have to think seriously about whether or not this extra overhead is worth it in your organization if you're running, if you have the hardware only to run what you're your normal workloads. Then in terms of precision and recall, how well are we doing on these synthetic attacks that I described earlier? So what we've got is the top line in blue is a description of, or the legitimacy score assigned to all of the synthetic attacks. And so the closer to the bottom it is the higher the legitimacy score. So a score of 100 says, this thing looks just like we predicted. We got every single feature nailed spot on. And a legitimacy score of 0 says we couldn't identify anything. It's completely anomalous.
What's the x-axis?
The x-axis is simply sorted in increasing legitimacy score, just to give us a smooth curve. The x-axis has no meaning, which is why there's no label on the x-axis. And what this shows is that there's a pretty wide range between the synthetic workload and the legitimate query workload. So we're getting a pretty good discrepancy between the two. I mentioned earlier that I would tell you how we pick a reasonable score. So what we did, I kind of lied when I talked about how we build a cross-feature analysis. In addition to a training and a testing phase, there's actually a tuning phase in the middle. So we do the training, but we hold out some of the data in order to tune the parameters. And the parameter that we care about here is what is that number that we're going to assign as being high enough in order to let the query run. And to figure that out, we then run some of the held back examples through, and we pick the threshold that gives us the optimal F score, the average or weighting of precision and recall. So in this particular case, the number 99.25 is the number that came back with the optimal F score. And if we look at those numbers, then our recall is 98.83%, so we're identifying more than 98% of the anomalous blue queries as being illegitimate, and our precision is 99.2%. So of the stuff that we've classified as illegitimate, we're right 99% of the time. We're only getting a handful of those red dots on the far left-hand side. As I said, this just proves that we're finding interesting patterns. We're effectively creating these really tight clusters in the high-dimensional space. So let's look at some real attacks. So same sort of presentation here. The blue is the actual attacks. The red are the legitimate examples. The reason you don't see 33 attacks here is when we put together this workload, the attack team didn't know what the legitimate workload looked like. So more often than not, they came up with some sort of query that they wanted to run that ended up having something completely anomalous about it and therefore being rejected trivially. So 22 of them were thrown away with a score of 0. And then of the remaining 11, they didn't get anywhere close to our threshold of 99.25. So if we're setting our threshold that way, we're in fact catching every single real attack, and the results were showing that we had about a precision of about 99% if there was an even number of attacks to legitimate cases. Hopefully in the real world your number of attacks isn't as high as your number of legitimate queries, so you will see a bunch of false positives as a result of doing something like this. And what actually happens is going to depend really on how heavily adversaries are banging on your system. And the one we were looking at, it's not accessible to the outside world, so the only people who can attack it, we think, are internal employees, and we hope that we don't actually see any of that. So it's a little hard to know exactly what would happen in the real world, but we think that we really have some good results there. So let me demonstrate what happens then in the real system to bring back to that original demo. So what we've got is the exact same web interface, but we've now plugged our software into the database on the back end. So when we run this query with the single quote, semicolon, dash, dash, the web application returns the connection is dropped, and so it says malicious activity was suspected. I'm not even going to process this particular query. So why does that work now that we've seen everything that was going on behind the scenes? Here's the actual decision tree that we built for a particular feature, which is the complexity of the where clause. So when we look at the query that gets assembled, select everything from core where ID equals this, and we've commented everything else out. The complexity of the where clause, according to the optimizer, is 7. And why is it 7? I have no idea how ID equals, my name is 7, that's the number it returns. A little bit of magic. But if we walk through this decision tree, the first thing we have to ask is, how many columns are being returned by the select clause? It's 129, we knew that from the attacks. So we follow this branch. 7 does not fall within this 11 plus or minus 0 range that we've identified as being what we expect to see. So the attack fails. What happens if we're a super user? We can now run any query we want. We don't have to rely on SQL injection attacks. And as an insider, I know that the system has all of these sorts of extra features in. It's built up the profiles, and it's trying to stop me. So as an attacker, I say, well, I'm going to need to get the where clause to look pretty much right. So instead of trying to run just the ID, I'm going to throw in this extra little bit to the query that I know from some other means, or I could just test each one of the states until I found the right one. Let's see if that works. Unfortunately, through its optimizer magic, the complexity of this one is only 10. It's missing something. So when I run through it, I end up seeing that 10 doesn't fall within the magic range of 11, and so even this super user who knew what's going on behind the scenes, at least the first attempt to find something that would run failed. Here's what the super user would actually have to do. And in order to construct this, what I did was I replicated the database on an unsecure machine, ran sample queries through the optimizer until I could, to get a feel for what plans were being run, both with a legitimate query and then with some sample attacks. And I found that I had to throw in some extra casts inside the query. Not that the casts do anything, but they magically increase the where clause size to 11 from 10. And now, as expected, when I run through this, it works. So, yes, we know we can't stop everything, but I think it's taken the super user a lot of inside knowledge. They have to know the exact schema of the database. They need to be able to set it up on some machine under their control with data that looks pretty legitimate in order for the statistics to look right. And they have to be able to then run all of these tests. And as they're testing their procedure to see if they actually got it right, each one of those things is putting a flag into the log, and hopefully somebody on the security side is watching those logs and saying, wait a second, why is one of our admin getting disconnected 50, 100 times? I probably got booted out of the system about 100 times before I found an attack that worked. And if security wasn't calling me to say what was up by then, we got bigger problems inside. So that was a look. Hopefully I've convinced you that at the very least we're on to something interesting in terms of identifying these anomalous, this anomalous activity. So when will this work, and when are you going to run into some trouble? So right now, the first caveat is we plug directly into the query processor. We've been using Postgres as our engine of choice because we have access to all the source code, and it's got a pretty good optimizer for us to play with. But that requires that we do have access to the source code. Our next iteration, and actually this changed since last Friday, our current iteration is deployed as an Oracle appliance. So all of the queries have to get channeled through this appliance. So it's an appliance that either lives on the same box but intercepts all of the queries as they come in, or it lives on a different box. They all get channeled through this appliance. As I mentioned before, this requires that you have this inter-process communication. So it's roughly twice the optimization cost. That could be a concern. There's also a security implication. If you're running the appliance, the trusted insider is going to know you're running the appliance. They're not going to connect to the appliance. They're going to try to connect directly to the database, and no amount of monitoring from outside the database is ever going to help you there. The other big caveat is the assumptions that we made. The first assumption is we assume that we have access to some sort of query workload. Now this can be because you have historical logs of known legitimate activity. If you're relying on that, you better have some way to verify that what you're looking at really does constitute legitimate activity. So there's a bit of a chicken and egg kind of problem going on there. What I'd actually recommend would be to obtain performance tests. So the people who are putting the system together hopefully have a development environment as well as a production environment. On the development environment, you're going to be running a whole bunch of tests to make sure that you can meet the demand that's going to be put on the production system. Those are all going to be, or at least you know which ones of those are legitimate queries that you want to go through. You can collect several thousand of these from the performance tests and use those. If you miss something that should be allowed to actually run, that means your performance tests weren't as representative as you thought they were, and you can go back to the team and say, hey, you need to add some more production tests, or they are representative and now you get good profiles based on that workload. And the last little wrinkle is we're expecting there to be a predictable workload. So we're talking here about transaction-style databases. Things where you're doing pretty predictable workloads. We're not looking at business intelligence applications. Business intelligence applications support a lot of ad hoc queries. A lot of times one query does not look like anything you've ever seen before, and if that's the sort of workload you have, no sort of anomaly detection is really going to help with a security issue because you're in a case where everything is anomalous, and it doesn't really matter how clever your techniques are. So just to wrap up and leave some time for questions or comments or clever ideas that you have that I've missed. First off, I hope I convinced you that relational databases are an important thing to protect. They're sitting behind many of our applications, and if you're not careful, it's not too hard to get a lot of information out of them. So we've got to secure these databases. We've got to do so both against the outsiders, who are largely the easier ones to protect against. You also have to protect against the insiders. So the approach that I've shown is first we build profiles of legitimate queries using this cross-feature analysis. And then as incoming queries arrive, we compare those against the profiles and detect anomalies. In most cases, we think those anomalies are things that are illegitimate activity. So this works against SQL injection, as I mentioned. It also helps protect against the insider threat, as well as many other forms of attacks. In terms of where we're going next, the first step we have to do is a red team exercise. So we've done this with some real attacks by a security team, and that only really leveraged what they were trying to do. They weren't actively trying to bypass all of the security mechanisms. So we'll set the whole thing up. But this time, we'll turn it over to anybody inside our company who wants to try to break in, and we'll put it on an unsecure OS. We'll make sure that the security on the web application is also unsecure. Basically, give them all of the benefits and see how often we're able to stop the attacks nonetheless. And then starting in October, we'll start looking at adapting these techniques to modifications where people are actually trying to update things or delete things, drop tables, all sorts of shenanigans. So let me wrap up with that, and I think I have just about 10 minutes for any sort of questions or comments.
Please use your microphone.
Yeah, please use your microphone. Press the button on your microphone. Ask the question.
One of the important aspects of security is not about only about preventing attacks, but also usability of the secure solution. So you talked about how to detect anomaly, anomalous SQL requests, but you didn't talk at the end of the solution how usability is, or is it preventing any legitimate requests also?
So let me go back to a previous picture. It'll take it just a moment because it has to redraw the graph each time. I showed this with just one threshold. In actuality, what we recommend doing is having two different thresholds. So one threshold that's put at the optimal F score, and anything that gets a higher legitimacy score than that, we're just going to let go through. You should probably do your normal auditing, whatever is reasonable, but we're just going to let everything go through that's above that, so that's going to allow almost all of the legitimate activity to go through. But you'll notice that there's some other values that would be flagged as illegitimate. So what we recommend is looking at your legitimate examples and picking a threshold where there's a big break that allows almost all of the legitimate examples to go through. And that depends it depends on your workload where you're going to see those values. You put a second threshold there. You simply deny anything that fails to meet that threshold. So everything in the top portion of the graph is stuff that would get thrown away categorically. And then there's that mid-range. Those are those question marks in the first sort of toy examples that I worked through. And there, what you probably want to do is allow the query to run, but flag it so that somebody can go through afterwards. And as a result, in terms of usability, what you're going to be doing is allowing basically all of the legitimate activity to go through. You'll have a pretty good understanding of how much legitimate activity you would be squashing. What it does, though, is it increases the workload on the security side because now they have that many more false positives to weed out or action items to follow up on because illegitimate stuff did go through.
There is another question on SQL injection. SQL injection is not necessarily is actually a problem of the language, since it is a declarative language and it has not been formally defined to have real checks and everything. So therefore, SQL injection is so successful. There have been work in because you only show only one paper in your related works. There are work in POPL. Maybe you look at POPL 2006 or 2007. That's on programming language community. They have defined type systems on how to check these attacks. So maybe implementing such solutions would be a better way to prevent these attacks at the SQL engine level than trying to look at such attacks as anomalous requests.
Yeah, so I actually only recently learned of some of that type stuff, which is why I haven't really worked it in. I don't know where it fits into the big picture. And absolutely, those are good ideas to follow up on. I think my understanding of those techniques is that they will help stop SQL injection. However, they're going to be configured like the rest of your security mechanisms, so they're not going to stop excessive privilege abuses or legitimate privilege abuses or privilege escalations necessarily. So if there's a way to get inside, then you're going to be able to bypass those mechanisms, and I think that we have a pretty good shot still of detecting anomalous insider behavior, and that was really the focus from the very beginning. Being part of the mission assurance package, our assumption is that the adversaries already have insider access, so just stopping the SQL injection is not sufficient from our perspective. Thanks.
Hi. By looking at a very naive application, which is the worst case of an application, you're actually looking at the best case for your detection system in a way, because that's where you'll catch the most anomalous activity. What if you were using instead your system to protect an application that's been built reasonably securely? Would you see still a lot of benefit from this system?
So if you're looking at something that has good security, that means most of the attacks will already fail. So finding enough attacks that constitute an interesting workload becomes that much harder. So in terms of the evaluation side, I think there is benefit to turning those off. because then what you can focus on, what the red team's activity has to become is, how do we get past this sensor? And then when you go to the real world, sure, you should still have those things on. You also commented that it makes us look better because
You catch more.
so certainly it does allow us to catch more, but if those zeros are caught by other mechanisms, we still have to look at those that did manage to bypass. So I think what it does is, more than anything, it changes the total number of attacks in your test.
Well, that's not all. I mean, when you do security, you're always balancing the cost of the added security versus
Yes.
the benefits. So what I'm asking in a way is, given the cost of your system, what are the benefits in a real world application that's being implemented reasonably securely? And how does
Right.
that compare?
And I don't have a good pat answer for that.
Okay.
It's certainly the case that with the appliance approach, if you had reason to believe that your system was well secured, then I don't think a 100% increase in the cost of optimization is worth the effort. I do think that if you're dealing with something where you can plug directly in and you're only paying the 50 microsecond overhead, that comes out to being just a few percentage points of performance implication, and at that point, you may as well. But in terms of what are the real dollars, in terms of cost and benefit,
The time of the transaction, but also training and
absolutely
tweaking.
And,
Yeah.
and I don't have a good answer for that because
Okay.
it's beyond what we've managed to look at so far.
Thank you.
Thanks.
This sort of builds on some of the same ideas, is that another cost to consider is for those false positives that are definitely denied because they're below your bottom threshold. What sort of, have you put in any thought into mechanisms to allow exceptions? How would that be handled?
Absolutely. I didn't mention it, but one of the things that we would recommend doing is setting up some special cases for these specific feature vectors that we know are legitimate, but for whatever reason weren't getting classified correctly as you're going through the tuning phase. You should pull those out and say, we're going to put some special cases in. If you see these specific things, go ahead and let them run. This example didn't show it very well, but a different application that we put together had the interesting feature that there were large numbers over in this left side. The tail was actually, there were more elements in this tail, but they corresponded to about 2 different plateaus where all of the feature vectors for those 2 plateaus were identical. So just by having those 2 exceptions, we would have stopped almost all of the false positives. But you're going to need some special cases, and as you start seeing some patterns, you may then want to work those in and make sure that they come out of the training phase as well.
Any other questions? Or does anyone see a better way to do this?
They're not going to answer that because they want to go out and publish.
Oh. Okay, well, let us thank our speaker then.